Welcome back to Science Corner, everyone. I am so excited for today's deep dive. We're going to be exploring the Earth's internal structure,
Journeying to the center of the Earth.
a place we can't physically visit, of course, but you, our amazing listeners, have provided us with some fantastic resources to work with, including Wikipedia articles about the Earth's crust, mantle, inner core, and outer core. Should be a fascinating journey.
Absolutely. Each layer is like a piece of a puzzle, and together they paint a picture of the dynamic forces that shape our planet. Let's start with the outermost layer, the one we're most familiar with, the Earth's crust. It might surprise you to learn that its most abundant element is oxygen.
Oxygen. Really? I always thought it would be some kind of heavy metal, not the stuff we breathe.
It does seem counterintuitive, but yep, 46.1% of the Earth's crust is oxygen. Of course, it's not just floating around as pure oxygen. It's bound up with other elements like silicon, which comes in at 28.2%, and aluminum at 8.23%.
So it's oxygen, but it's combined with other elements to form the rocks and minerals we see around us.
Okay, that makes sense. But, when we talk about the Earth's crust, we're actually talking about a pretty thin layer, right? Compared to the rest of the Earth.
Yeah, incredibly thin, relatively speaking. It ranges from just a few kilometers thick under the oceans to around 70 kilometers thick under mountain ranges. Imagine an apple. The crust would be like the skin.
Wow, that puts things into perspective and makes you realize just how much is going on beneath the surface, huh? What lies beneath the skin, this Earth's crust.
Well, next we encounter the mantle. This is a massive layer, mostly silicate rock, and it makes up a whopping 84% of Earth's volume.
84%, that's huge. So what's going on down there in this rocky realm?
While it might seem like it's all solid rock, the mantle actually behaves like an incredibly viscous fluid over geologic time. Think super thick caramel.
Okay, interesting analogy. So it's constantly in motion, even if it's at a super slow pace, right? Exactly. Hot material rises in plumes, while cooler material sinks, creating a continuous cycle of motion known as convection. And, this is what drives plate tectonics.
Oh, right. The movement of the continents, the formation of mountains, all that.
Wow.
Wow, the Earth's mantle is much more dynamic than I imagined. This slow dance has shaped the continents and oceans as we know them. Okay, I'm ready to venture deeper. Tell me about the Earth's core, this mysterious heart of our planet.
The core is actually divided into two parts, the outer core and the inner core. The outer core is liquid, a swirling ocean of molten iron and nickel.
Molten metal. How hot are we talking about here?
Incredibly hot. Temperatures range from 4,000 to 8,000 Kelvin. To put that in perspective, that's hotter than the surface of the sun.
That's just mind-boggling. And this liquid metal, this outer core, is what generates the Earth's magnetic field, right? I mean, that's just incredible.
It is. The movement of this liquid iron, coupled with the Earth's rotation, generates electric currents. And these currents create the magnetic field that surrounds our planet.
So the Earth is like a giant electromagnet, with its molten heart powering an invisible shield that protects us from harmful radiation from space.
Wow. I'm starting to appreciate just how dynamic and complex the Earth is beneath the surface. We've gone from a thin, oxygen-rich crust to a churning mantle, and now a molten outer core generating a planetary magnetic field. So what awaits us at the very center, the inner core?
The inner core, despite being even hotter than the outer core, is actually solid. The immense pressure at the center of the Earth forces the iron and nickel into a solid state, even though the temperatures exceed 5,000 Kelvin.
So we've got this solid, super hot iron ball at the very heart of our planet.
That's a pretty good way to picture it, and it's slowly growing over time as the outer core cools and solidifies, adding to its already impressive mass.
This deep dive is full of surprises. I'm seeing the Earth in a whole new light. But before we move on, tell me, is there anything else going on in the inner core? I mean, besides just, existing as a giant, hot, solid ball. Actually, there's a really intriguing detail about the inner core that we need to talk about. It's called seismic wave anisotropy. You see, scientists have discovered that seismic waves, those vibrations that travel through the Earth after earthquakes, don't travel through the inner core at the same speed in all directions.
So it's not uniform. What does that tell us?
Well, this difference in wave speed, this anisotropy, suggests that the inner core has a kind of grain to it, like a piece of wood. The iron crystals in the inner core are preferentially aligned, meaning they're pointing in roughly the same direction. And this alignment affects how seismic waves travel through it.
Okay, let me see if I understand this. We have the solid inner core, mostly iron and nickel, under unimaginable pressure and heat. But it's not just a random jumble of atoms. The iron crystals are lined up in a specific way. Fascinating. What could cause that kind of alignment deep inside the Earth?
It's still an area of active research, but the most widely accepted explanation is that the slow movement of iron within the inner core, perhaps driven by convection or the influence of Earth's rotation, causes the iron crystals to align themselves over time. It's like a slow motion crystallization process that's been happening over millions of years.
So even in the seemingly solid heart of our planet, there's change and movement happening on a timescale that's, well, hard to grasp. Amazing.
That's the beauty of studying Earth's interior. It challenges our perception of time and reveals the dynamic processes that have shaped our planet over billions of years. And we've only scratched the surface.
Welcome back to Science Corner. Ready to go a little deeper into this whole Earth's mantle thing?
Oh, absolutely. In part one, we traveled all the way from the Earth's crust down to the inner core, learned some pretty amazing facts about our planet. Now I'm ready to explore this mysterious layer that makes up the bulk of our planet's volume, the mantle. The mantle is where it's at. It's a region of intense activity, even though things move really slowly, like millimeters per year. But it's what drives plate tectonics. It's what shapes the continents and the oceans.
Right, right. Okay, so remind me again, what exactly is the mantle made of? It's rock, right? But what kind?
The mantle is mainly composed of silicate rock. That means rock that's rich in silicon and oxygen. The most common rock type in the upper mantle is peridotite, a mix of minerals like olivine and pyroxene and garnet.
Okay, yeah, those names ring a bell, vaguely, from my rock collecting days back in the day. But I'm guessing the mantle isn't just one big blob of peridotite, right? There must be some variations as we go deeper.
You're so right. The mantle is far from uniform. In fact, it's divided into a few different layers based on how seismic waves travel through them, and also based on what minerals they're made of.
Ah, yes. Seismic waves. Those vibrations that travel through the Earth after earthquakes. We talked about how they help us understand the core. Now they're giving us insights into the mantle as well.
Exactly. Scientists analyze how seismic waves speed up or slow down as they pass through different parts of the Earth. That's how they can map out the major layers of the mantle.
Okay, so break it down for me. What are these mantle layers?
Yeah.
And what makes each one unique?
All right, so starting from the top, right below the crust, is the upper mantle. It goes down to a depth of about 410 kilometers, and as I said, it's primarily made up of peridotite. But the mineral composition changes a bit as we go deeper.
How so?
Well, in the uppermost part of the upper mantle, the aluminum-bearing mineral is plagioclase. But as we go down, the pressure increases, and plagioclase becomes unstable. So it transforms into a different mineral called spinel.
So the minerals themselves change under pressure.
Exactly. They're constantly adjusting their structure and composition in response to the changing conditions. It's like a game of mineral Tetris.
Ah, that's a great way to put it. It's like the mantle is a giant metamorphic laboratory. Okay, so what happens below this upper mantle layer? Does this mineral switcheroo continue?
You bet it does. Below the upper mantle is what we call the transition zone. It goes from about 410 kilometers down to 660 kilometers. And this is where things get really interesting.
All right, lay it on me. What's so special about this transition zone?
The transition zone is where we see some pretty dramatic changes in mineral structure. For example, the olivine, that was such a big part of the upper mantle, it transforms into two new minerals. They're called wadsleyite and ringwoodite.
Wow, even the names sound exotic. What's so special about them?
The cool thing about wadsleyite and ringwoodite is that they can hold a lot more water within their crystal structure compared to olivine.
Wait, water? In the mantle? I thought it was solid rock all the way down.
It's mostly solid, yes, but there's actually a surprising amount of water locked up in those mantle minerals, especially in the transition zone. Some scientists think there might be more water in the mantle than in all the oceans on the surface combined.
No way. That's incredible. So we're talking about a lot of water, not just a little bit.
Exactly. And this has led to some really interesting theories about the role of water in mantle processes. Things like the generation of magma and the movement of tectonic plates.
My mind is blown. Hidden water, mineral transformations, a mantle that's moving like a slow-motion river of rock. Okay, what's next? What's below this water-rich transition zone?
Below the transition zone, starting at a depth of about 660 kilometers, we reach the lower mantle. This layer is huge. It extends all the way down to the core mantle boundary, almost 3,000 kilometers down.
Wow, that's a long way.
Yeah.
What's the rock situation in this lower mantle layer?
Well, it's a realm of extremes, extremely high pressure, extremely high temperature. The main minerals down there are bridgmanite and ferropericlase. Bridgmanite, by the way, is thought to be the most abundant mineral on Earth.
Bridgmanite, huh? Another exotic name. Tell me more about this mineral superstar.
Bridgmanite has a really dense crystal structure. It's tightly packed, which allows it to remain stable even under those incredibly high pressures. It's amazing to think that this one mineral makes up such a huge portion of our planet.
It's like the unsung hero of Earth's interior. So Bridgmanite and Ferropericles are the big players in the lower mantle. Any other surprises down there?
Actually, yes, in the lowermost part of the lower mantle, right above the core mantle boundary, there's a mysterious zone called the D layer.
D. Huh. Sounds like a secret code. What makes it so mysterious?
It's a pretty thin zone, only about 200 kilometers thick, but it has some unusual seismic properties that suggest it might be compositionally different from the rest of the lower mantle.
So it's like a hidden layer within a hidden layer. What do scientists think this D layer is made of?
There are a few different theories. Some scientists think it might be a graveyard of subducted slabs, like remnants of old oceanic crust that have sunk all the way down to the core mantle boundary.
Like a recycling bin for Earth's crust?
Kind of, yeah. These slabs, which were once part of the surface, might be piling up at the bottom of the mantle, forming a distinct layer with its own unique properties. It's a cool idea that pieces of Earth's history are preserved down there.
That's wild. Are there any other theories about the D layer?
Another possibility is that it's a zone where bridgmanite goes through another transformation. Maybe it transforms into a mineral called post-perovskite, which has an even denser structure that can handle those extreme pressures.
Okay, I'm seeing a trend here. The deeper we go, the more extreme the conditions and the weirder the minerals get.
That's Earth for you. Always full of surprises.
I'm loving this deep dive.
Okay.
Before we move on to the outer core, I want to go back to something you mentioned earlier, the water that's locked up in the mantle minerals. How does that water get down there in the first place?
It's all thanks to subduction. Remember how we talked about tectonic plates colliding?
Yeah, that's driven by the mantle convection, right?
Exactly. When an oceanic plate collides with a continental plate, the denser oceanic plate sinks down beneath the continental plate. That's subduction.
Right, and that's where the water comes in.
Yes. Oceanic plates are full of water, both in the sediments and in the rocks themselves. As they descend into the mantle, they take this water with them.
It's like a giant water slide delivering water from the oceans to the Earth's interior.
Great analogy. And as the subducting plate goes deeper, the increasing temperature and pressure force the water out of the rocks and minerals.
And then what? Does it form like underground lakes?
Not exactly. It doesn't exist as a liquid in the mantle. Instead, it gets incorporated into the crystal structure of those mantle minerals, especially the ones in the transition zone, wadsleyite and ringwoodite.
Oh, so the water molecules actually become part of the mineral. It's hard to imagine water existing like that.
It's pretty amazing. And this process of water getting into the minerals, it actually plays a big role in controlling whether the mantle melts or not. Water acts as a flux, which means it lowers the melting point of the rocks.
So if there's more water, it's easier for the mantle to melt.
That's the basic idea. And when the mantle melts, it creates magma, which can then rise to the surface and erupt as volcanoes.
Wow. So this water, it hitches a ride on a subducting plate, and then it could eventually cause volcanic eruptions.
It's all connected. It highlights how all these Earth systems are interconnected. The plates move, the water gets subducted, the mantle melts, and volcanoes erupt. And remember, this is all happening over millions and billions of years.
It's amazing to think about these processes happening over such a long time. This is what I love about Science Corner. We get to piece together the story of our planet and discover all these incredible things.
And we're not done yet. There's still more to explore.
I can't wait. Welcome back to Science Corner. We're about to wrap up our deep dive into the Earth's internal structure. And for the grand finale, we're heading into the Earth's outer core. This is where things get really interesting.
Get ready for a wild ride. The outer core is basically a giant sphere of liquid iron and nickel. It's over 2,000 kilometers thick. It's swirling around under incredible pressure.
I can't even imagine what it would be like down there, this molten world beneath our feet. And this is what creates our planet's magnetic field, right? That invisible force that protects us from the sun.
You got it. The Earth's magnetic field is essential for life as we know it. It acts like a shield, deflecting those charged particles that come streaming from the sun. It stops them from ripping away our atmosphere. Without it, well, Earth would be a very different and much less friendly place.
So we owe the outer core a big thank you for making Earth habitable. But how does this work? How does a ball of liquid metal actually create a magnetic field?
It's a process called dynamo action. It involves a lot of complex interactions between heat and motion and electricity. Basically, the outer core is constantly in motion. It's driven by convection currents. Hotter, less dense material rises up, while cooler, denser material sinks down.
Like a giant lava lamp, but with molten iron instead of colorful blobs.
Exactly. And as this liquid metal moves around, it carries electric currents with it. Those currents flow through the conductive iron-nickel alloy, and that generates the magnetic field.
Okay, so the movement creates the magnetism, but the Earth's magnetic field isn't just some random thing, right? It has a specific structure with a north pole and a south pole. Where does that come from?
That's where Earth's rotation plays a crucial role. You see, we have this thing called the Coriolis effect. It
Hmm.
causes moving objects to curve because the Earth is spinning, and it has a huge impact on those convection currents in the outer core. It makes them twist and spiral so they flow in a more organized way.
Wait, the Coriolis effect, the same thing that affects weather patterns, that's also shaping the Earth's magnetic field.
One and the same. The combination of convection and electric currents and Earth's rotation all work together to create a self-sustaining magnetic field. And it acts like a giant dipole magnet with a north pole and a south pole.
So we have this dipole field that extends way out into space, forming what we call the magnetosphere, our planet's magnetic shield.
That's incredible. Now, I was reading that Wikipedia article about the outer core, and it mentioned that it's not just pure iron and nickel. There's some other elements in there too, right? That's right. Scientists think there's a small percentage of lighter elements present as well. Things like sulfur, silicon, oxygen, even hydrogen. These lighter elements probably came from the early Earth, and they play an important role in the dynamics of the core.
Really? What kind of difference do they make?
Well, for one thing, they affect the density and buoyancy of the outer core, so they influence those convection patterns we were talking about. And they also play a part in the chemical reactions that are happening within the core. All of this helps to keep that dynamo process running, keeping our magnetic field strong.
It's like a finely tuned recipe with just the right mix of ingredients to make it all work. Well, this has been an amazing journey. We started at the surface with the solid rock beneath our feet, and we've traveled all the way down to the swirling molten metal of the outer core.
It's amazing to think about all the complex processes that are happening deep inside our planet. And it's a reminder that there's still so much more to discover about the world we live on.
Absolutely. And a big thank you to all of our Science Corner listeners for joining us on this incredible deep dive. We'll see you next time as we continue to explore the wonders of science.